Okay, for today's class, Unit 8, we are studying reaction-diffusion processes. And for the class today, we read Alan Turing's paper, The Chemical Basis of Morphogenesis. As a child, he was very interested in chemistry. Then he went into mathematics. Then he went into developing computers. Then he went back to chemistry with this knowledge. And he was trying to understand how biological organisms construct themselves. And he came up with some equations that could describe chemical reactions that did some interesting things. I'm going to start off by showing you some videos about the BZ reaction, a reaction discovered by Boris Belousov in 1956, long after Alan Turing had died. The first video brings up some interesting issues about thermodynamics. According to the second law of thermodynamics, because there are more ways for matter to be all mixed up and in different states and disorganized, than there are ways for matter to be arranged in some sort of order. It's more statistically likely that systems will move to a more disordered state. So it would be somewhat surprising if a system spontaneously became more ordered, like a box of gas that has completely fast, hot molecules on one side and completely slow, cold molecules on the other side. Remember, we've already talked about this with Maxwell's demon. Okay, here's the video.
Early in the 1950s, a Russian chemist by the name of Boris Belousov reported one of the weirdest reactions that has ever been seen in chemistry. It was a reaction which seemed not to be able to make up its mind. Let me show you. Now I'm pouring in a little bit of hydrogen peroxide into this mixture, and you can see that yellow color as iodine is produced. Then it turns deep blue, and then the whole process goes back to yellow again. I mean, this reaction flip-flops between these yellow and these blue states. To the chemists who read the report, this seemed a complete outrage. Could this reaction actually represent a violation of the second law of thermodynamics? Let me explain. In a typical chemical reaction, in which A is reacted with B, what we might do is actually get some kind of product. And in this case, you can see this beautiful pink color. Well, that reaction is effectively over. We've formed the product, and that's it. And when chemists think about a reaction like this, they imagine that the reaction is traveling through a landscape, from the starting materials high up in the mountains, down to the much lower energy, much more dispersed plains where the product lies. This ball provides a really good analogy of the way in which this second chemical reaction went. When we place it at the top, and as the reaction proceeds, the reaction essentially rolls down a slope until it reaches the bottom. And when the ball is at the bottom, we all know there's no prospect of it ever coming back up to the top. And the same applies to our pink solution. Our pink solution has reached the bottom of that chemical slope. Now, what Belousov discovered was not a simple reaction in which A and B are combined and simply form a product. What he'd seen was the path that his chemical reaction was taking on the way down the slope. Now, the way to illustrate this is not to use a ball, but instead to use one of these simple toys. This is called a slope walker. What he does is he walks down the slope, effectively going yellow, blue, just like our reaction. But in the end, he gets to the bottom. And at that point, our reaction is over. And therefore, this is no violation of the second law. We have a reaction which starts at the beginning and finishes at the end. When we look back at Belousov's reaction, you can see that it's now gone a steady blue. The reaction is over. And in many ways, these reactions that Belousov found are a metaphor almost for life itself.
Now we're going to look at another video showing the same reaction, chemical reaction, but this time they're going to pour the liquid into a shallow dish, and so it's going to be a thin layer of liquid. And you will notice that the BZ reaction looks quite similar to a Turing pattern.
And then I'll give it another shake. And now it's going brown, which is also a good sign. And now we'll just wait for a second and see if it will do what I want it to do. And in fact, it's already started. Of its own accord, little blue dots are appearing. And those dots are spreading and forming blue patches. And as the patches grow, inside them we see little red dots which grow, and inside those are blue dots which grow. And the whole thing just keeps growing and spreading, and this amazing pattern appears like magic from nowhere. But it's not magic, it's symmetry breaking. The uniform symmetry of the stirred up, shaken up dish is unstable. It won't stay that way. Tiny little bubbles, little specks of dust, something start out those blue patches. And once they've started, we just get these beautiful patterns which grow and grow.
By the way, that was Ian Stewart giving the free Christmas Day lecture, a tradition started by Michael Faraday in the 19th century. Okay, so right before Alan Turing got started writing this paper, The Chemical Basis of Morphogenesis, he read Darcy Wentworth Thompson's On Growth and Form, which you read the introduction to, and he also read Conrad Howell Waddington's book, Organizers and Genes. The first video on discussing thermodynamics and about energy flowing downhill, that was actually a reference to Waddington. Now, Waddington had a theory about biological morphogenesis, and he illustrated his theory with this analog model, which he called the epigenetic landscape. We've talked about biological chemical processes, how sometimes they're very complicated and involve a number of different chemical transformations. If a chemical reaction is starting at the top of that hill there, and it goes down the hill, it's flowing through its various transformations. Two different chemical pathways may compete for one of the chemicals, and depending on which chemicals are available or not, the chemical reactions might flow down one valley or another. Waddington hypothesized that there was some mechanism going on that could result in this bifurcation of different biological processes, and that might be how genes work. His book, again, was called Organizers and Genes. Alan Turing invented the most practical tool humans will likely ever wield. And yet his engineering successes were driven by a very impractical desire to understand the nature of human intelligence. In the 1950s, after proposing his model for the self-learning computer, which we've already talked about, Turing's thinking began to take what might be called, in hindsight, a second-order cybernetics or artificial life turn. He began conducting experiments and studies in mathematical biology. Turing used the world's first commercially manufactured electronic computer, which was installed at Manchester University, to model biological growth. That's the first thing he did with this new computing power. Turing discovered the spontaneous processes by which unorganized systems organize themselves without interference, without any external selection. Waddington had suggested to Turing that development simply falls into order somehow, flows down the path of least resistance. It was Turing who suggested that an instability, some sort of chance pattern, not an inducer specifically designed for that function, could initiate the flow from less order to more order, or from chaos to differentiation, from being all mixed up to being separated. So let me try to describe the chemical reaction as best I can. The reactions typically involve a number of different chemicals. Let's say chemicals X and Y react to produce Z. Then Z and A react to produce Y. The first reaction depletes Y and the second reaction increases Y. So they're alternating back and forth between decreasing Y and increasing Y. To put it a little bit differently, there's an activator that can catalyze its own production and that of its own inhibitor. So if you have an inhibitor that diffuses away from the center of the reaction faster than the activator does, then you get this ring, this wave spreading out from the center and leaving behind it areas of activation. And that's how spatial patterns can be created by chemical reactions. There is a kind of contradiction or paradox in these processes, which are both self-creating and self-constraining at the same time. It reminds me of the syllogism that Turing came up with as a kind of a joke, because he had a pretty good sense of humor even after he was arrested and convicted for being a homosexual. It's a version of the Cretin's liars paradox. All cretins are liars, said the Cretin. Turing believes that machines think. Turing lies with men, therefore machines do not think. There is, of course, a pun on the word lie here. Probably a main shortcoming with present-day computers, which do not take advantage of the kind of research that Alan Turing was starting when he died, is that they're just not very good with language. They're not good with language because they don't get irony, they don't get they don't understand new metaphors, puns, or jokes. Language is fundamentally elusive. It's always pointing to something else other than what it is. It's always significant of something else. It's not literal. The fact that Siri could never get a joke, like the syllogism, is not because there's not world enough in time to train the network. A computer's lack of a sense of humor is symptomatic of the essential difference between AI and biological intelligence. But I don't think it's impossible to someday design computers to be able to get jokes. It's hard to imagine a formalism that is both digital and symbolic and also uses some sort of formula for interpretive signs. I want to show you an example which I hope will help you imagine that kind of symbolic system that can also get jokes. And this is an analog for a kind of chemical reaction. In this model, I try to incorporate both digital characteristics of a code and analog characteristics of a code. That the physicality of these letters themselves and the very shape of them is going to matter. They're not just arbitrary symbols. This is a clip from an old video.
Say we have a molecule that looks like an L and a molecule that looks like a T. We have both upside down and right side up letters. If two L's or two T's meet up, nothing changes because they can't interact. Also, if you combine a T and an L in certain orientations, still there's no change. But when T's and L's meet and combine in other ways, they can interact and undergo change. For instance, if a right side up T joins with an upside down L, the T can turn into an upside down L. If an upside down L meets up with a right side up T, the L can turn into a T. It depends on the orientation when they happen to meet up. More T's might be produced or more L's depending on how things go. The way they happen to meet up is just by chance. The production of new L molecules or new T molecules is equally likely, and you would think that this reaction scenario would just tend to kind of average itself out, but that's not what happens. Instead, differentiation occurs. If L equals black and T equals white, the random mix might go from an all-over gray pattern to a black and white spot pattern. This is because T clumps have produced more T's and L clumps have produced more L's. You could say that the clumps are self-sustaining systems.
I cut myself off there because in that video I was making a slightly different point than the one I'm making now. The point I want to make here is that there are simple local rules that are determining the reactions. Those rules involve whether or not the opened end or the closed end of the letters are meeting up. And this is meant to be an analogy to the way that chemicals have physical properties that may or may not happen to meet up as they float around in their environment. The upside down T here is metaphorically like an L. It turns into an L. The material qualities of these T and L-like signs, the relative similarity and proximity of these signs, can lead to a collective activity, emergent spot patterns that can't be predicted by calculating the number of different L's or T's in the system. It's by chance where a white spot or a black spot may emerge or where it'll remain a gray pattern. What happens is really determined by the local context. And this is similar to the way that the meaning of any piece of language is determined by the local context. Now let's think about how a pun might be possible in this system. Let's say that there's a type of molecule that looks like a Times New Roman font L. And because of its similarity to that weird L-shaped sign we've been discussing, it can function as if it were that L-shaped sign. All new signs discovered by a biological system must be recognizable to its already existing sign reading system. And this new L meets that criteria, even though it's kind of a mistaken generalization. The outcome of this new L and upside down T binding might mean that the system has a new way of making a meaning that it didn't have before. The new L is like a pun. So that's just one way to imagine how the various physical qualities of something, L's or T's, might make a difference in the outcomes of events and processes. So that is a kind of process that would require a qualitative evaluation. But we wouldn't say that this process is subjective in the sense of not verifiable or not objectively true. Although the specific outcomes of a process like this would be unpredictable, you could still look back at the process after the fact and describe what happened in terms that would be formulaic. Let me relate this now to the conspiracy theory narratives that we studied. Sometimes, in some cases, the meaning that was made by a conspiracy theorist might have been based on kind of like something like a pun, in that information was interpreted according to a rather unusual or unorthodox rule. Esenia's analysis of that might be considered a kind of formulaic description of the mechanisms that can be uncovered to explain that interpretation if, for example, the same kind of mechanism is being used over and over again. She identified 4 possible mechanisms describing the flat earth conspiracy theory. 1, religion was a mechanism used to interpret various facts. Secondly, radical subjectivity was sometimes overvalued. The subjective perspective was overvalued. 3, anomalies were overvalued, and 4, authority was overvalued. So the important thing in identifying the mechanisms that are being used to make unorthodox interpretations, make puns out of facts, is to be able to actually identify the mechanism that's being used and show examples of its usage. If you can do that, then I think your qualitative description of the group behavior or the behavior of individuals would have some relative objectivity. We're not quite done with Alan Turing and reaction diffusion, but I will segue into a different aspect in the next unit, Unit 8, when we discuss novelty and emergence.